Tonight, we're going to talk about something that's going to completely reshape how you think about size, about distance, about everything you thought you knew about what it means for something to be big. We're going to explore the largest object ever discovered in the universe. And I have to warn you right now, by the end of this, you're going to look at the night sky differently. You're going to understand something that most people never think about, something that makes even galaxies look like specks of dust. If you enjoy these deep explorations into the cosmos, consider subscribing or hitting the like button. It really helps the channel grow and allows me to keep making content like this. Let's begin with something familiar. Your house. The average house in America is about 2,500 square feet. That's a space you can walk across in about 30 seconds. You know every corner of it. This is a scale that makes perfect sense to your brain because you experience it every day. Your brain evolved to understand spaces like this, spaces you can see, spaces you can walk through. A football field, including the end zones, is 360 feet long. You could walk from one end to the other in maybe 2 minutes. A mile is 5,280 feet, about 17.5 football fields laid end to end. Most people can walk a mile in about 15 to 20 minutes. These are distances that feel substantial but achievable. The distance from New York to Los Angeles is about 2,800 miles. That's a 5-hour flight, or about 40 hours of driving if you somehow never stopped. The circumference of Earth at the equator is about 24,901 miles. If you could drive around the entire planet without stopping at highway speeds, it would take you about 383 hours, almost 16 days of continuous driving. But here's the thing. Compared to the scale of the solar system, Earth is tiny. And compared to the scale of the galaxy, the solar system is tiny. And compared to the largest structures we've discovered, the galaxy is tiny. We're about to climb a ladder of scales, each rung making the previous one look microscopic. The Moon is about 238,855 miles from Earth. When the Apollo astronauts traveled to the Moon, they were going farther than any human had ever gone before. The journey took about 3 days at speeds of roughly 24,000 miles per hour. The fastest you've probably ever traveled is in an airplane, maybe 500 miles per hour. The Apollo spacecraft were moving nearly 50 times faster than that, and it still took 3 days to reach the Moon. The distance to our local star puts all of this in perspective. Our star is about 93 million miles from Earth. If you could somehow drive there at highway speeds, 65 miles per hour, non-stop, it would take you about 163 years. You'd have to pass the driving to your children, who would pass it to their children, who would pass it to their children, and somewhere around your great-great-great-grandchildren, the car might finally arrive. Light travels at about 186,282 miles per second. Every single second, light covers 186,282 miles. When you flip a light switch, the light reaches your eyes essentially instantly because the distance is so short. But when you look at our star, you're seeing light that left its surface about 8 minutes and 20 seconds ago. If something happened on the surface of our star right now, we wouldn't know about it for more than 8 minutes. Because of these enormous distances, astronomers use a measurement called the light year. Despite having the word year in it, a light year is not a measure of time, it's a measure of distance. It's the distance that light travels in 1 year. Here's the math. Light travels 186,282 miles every second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. If we multiply all of these together, we get approximately 5.88 trillion miles. The nearest star to our solar system, other than our own star, is called Proxima Centauri. It's a small red dwarf star, about 4.24 light-years away. That means the light you see from Proxima Centauri tonight left that star over 4 years ago. It's been traveling through the darkness of space for more than 4 years, covering nearly 25 trillion miles to reach your eye tonight. Within about 16 light-years of our solar system, there are approximately 50 stellar systems. This region of space, this sphere about 32 light-years across, is our local stellar neighborhood. And in cosmic terms, it's microscopic. The Milky Way galaxy, our home galaxy, is roughly 100,000 light-years across. The galaxy is about 23,500 times wider than the distance to our nearest stellar neighbor. And our galaxy contains somewhere between 100 billion and 400 billion stars. Each of those stars is like our own star, a massive ball of hydrogen undergoing nuclear fusion, potentially with its own system of planets orbiting around it. Our solar system is located about 26,000 light-years from the center of the Milky Way. We're in one of the spiral arms. When you look up at the night sky and see that faint band of light stretching across the darkness, you're seeing the disk of our galaxy edge on. You're seeing hundreds of billions of stars so distant that their individual lights blur together into a continuous glow. The star at the center of our solar system orbits the center of the Milky Way at a speed of about 515,000 miles per hour. But the galaxy is so vast that even at this speed, it takes about 225 to 250 million years to complete a single orbit. The last time our solar system was in its current position in the galaxy, dinosaurs hadn't evolved yet. The Earth was in the Triassic period. Since then, the dinosaurs evolved, dominated the planet for over 160 million years, went extinct, mammals took over, primates evolved, humans appeared, built civilizations, invented technology, and looked up at the stars. And we've only just now completed one lap around the galaxy. Now, the Milky Way is not alone. The Milky Way is part of a collection of galaxies called the Local Group. The Local Group contains more than 80 known galaxies. The three largest members are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. The Andromeda Galaxy is about 2.537 million light-years away. When you look at Andromeda in the night sky, and you can see it with your naked eye if you know where to look, you're seeing light that left that galaxy over 2.5 million years ago. When that light began its journey toward your eye, our ancestors hadn't evolved yet. Everything you know about human civilization has happened while that light was traveling through space toward you. The Local Group is about 10 million light-years across. That's 100 times the diameter of the Milky Way. And yet, in the grand scheme of things, the Local Group is a tiny structure. The Local Group is part of a larger structure called the Virgo supercluster. A supercluster is a group of galaxy clusters, and galaxy groups bound together by gravity. The Virgo supercluster contains at least 100 galaxy groups and clusters, including our own Local Group. It's about 110 million light-years across. In 2014, astronomers redefined our cosmic address by discovering that the Virgo supercluster is just a small lobe of an even larger supercluster called Laniakea. The name comes from Hawaiian words meaning immense heaven. Laniakea contains about 100,000 galaxies and stretches about 520 million light-years across. To put that in perspective, if the Milky Way were the size of a quarter, Laniakea would be about the size of the United States. Laniakea is defined not just by the galaxies it contains, but by how those galaxies move. All the galaxies in Laniakea are flowing toward a region called the Great Attractor, a gravitational anomaly located about 250 million light-years away in the direction of the Centaurus constellation. Now, you might think that Laniakea, with its 520 million light-year diameter and its 100,000 galaxies, would be among the largest structures in the universe. But it's not even close. This brings us to the cosmic web. The universe is not evenly distributed. Galaxies aren't scattered randomly through space like confetti thrown into the air. Instead, they're organized into an incredibly complex structure that scientists call the cosmic web. Think of a three-dimensional spider web stretching across the entire observable universe. The strands of this web are called filaments, and they're made of galaxies, galaxy clusters, gas, and dark matter. Where filaments intersect, you find massive galaxy clusters containing thousands of galaxies. And between the filaments are enormous empty regions called voids, where almost nothing exists. This cosmic web structure emerged from tiny variations in the density of matter in the early universe. Shortly after the Big Bang, matter wasn't perfectly evenly distributed. Some regions were ever so slightly denser than others, maybe by 1 part in 100,000. But over billions of years, gravity amplified these tiny differences. Denser regions pulled in more matter, became denser still, and pulled in even more matter. Less dense regions became emptier as their matter was pulled toward the denser areas. The cosmic web we see today is the product of 13.8 billion years of gravitational evolution. Dark matter, which makes up about 27% of the universe, created the scaffolding on which all visible matter hangs. Dark energy, making up about 68%, is driving the acceleration of the universe's expansion. Ordinary matter, the stuff made of atoms, the material that makes up everything we can see and touch, accounts for only about 5% of the universe. The interplay between these components shaped the cosmic web into what we observe today. Galaxy filaments are among the largest known structures in the universe. A single filament can be hundreds of millions of light-years long, containing thousands of galaxies strung out like beads on a cosmic necklace. But even filaments aren't the largest structures we've found. The Great Walls came next in our understanding. The first Great Wall was discovered in 1989 by American astronomers Margaret Geller and John Hucra. They were mapping the positions of galaxies in a slice of the sky. What they found shocked them. Instead of a random distribution of galaxies, they saw a massive sheet of galaxies stretching across their survey. This structure, which they called the CFA, Two Great Wall, was about 500 million light-years long, 300 million light-years wide, and about 15 million light-years thick. But the CFA Two Great Wall was just the beginning. As astronomers mapped more of the universe, they kept finding bigger structures. In 2003, astronomers discovered the Sloan Great Wall, named after the Sloan Digital Sky Survey that found it. The Sloan Great Wall is approximately 1.37 billion light-years long. Light would take 1.37 billion years to travel from one end to the other. The Saraswati supercluster, discovered in 2017, is about 652 million light-years across and contains about 400 galaxies arranged in a massive wall-like structure. It's located about 4 billion light-years away from us. The South Pole Wall, discovered in 2020, is a massive filament of galaxies stretching at least 1.4 billion light-years across. It sits behind the plane of the Milky Way, in a region of the sky called the zone of avoidance, where gas and dust from our own galaxy block our view. For years, astronomers debated which structure held the record for largest. The Hercules Corona Borealis Great Wall, discovered in 2013, was long considered a contender. It was identified by analyzing the distribution of gamma-ray bursts and appeared to span up to 10 billion light-years across. However, its status has remained controversial. Some scientists questioned whether it was really a single connected structure or several separate structures that happened to be aligned along our line of sight. Others suggested the apparent clustering might be a statistical artifact from the gamma-ray burst data. But in early 2025, astronomers made a discovery that settled the debate about what holds the record for the largest confirmed coherent structure in the observable universe. They found Quipu. Quipu has an estimated mass of about 200 quadrillion times the mass of our star. Written out, that's 200 quadrillion solar masses. If you tried to count to that number, counting one per second without stopping, it would take you about 6.3 billion years. The Earth would be uninhabitable before you finished counting. The name Quipu comes from the ancient Incan recording system that used knotted cords to store information. The astronomers who discovered it chose this name because the structure resembles a complex network of interconnected threads, with galaxy clusters forming the knots along the cords. It's a fitting name for something so intricate and vast. What makes Quipu particularly significant is that it's a confirmed coherent structure. Unlike the Hercules Corona Borealis Great Wall, which was identified through indirect methods and remains debated, Quipu was detected through X-ray emissions from the hot gas that pervades galaxy clusters. This gas, heated to millions of degrees by the gravitational collapse that formed the clusters, emits X-rays that we can detect from Earth. The pattern of X-ray emissions reveals the physical connections between the clusters, confirming that they're part of a single enormous structure rather than an accidental alignment. The 68 galaxy clusters that make up Quipu aren't randomly distributed. They're arranged along filaments of dark matter that stretch between them, connected by bridges of hot gas and gravitationally bound into a single system. Each of these 68 clusters is itself a massive structure, containing hundreds or thousands of galaxies and trillions of stars. Together, they form something almost too large to comprehend. The discovery of Quipu challenges our understanding of how the universe evolved. According to standard cosmological models, structures this large shouldn't be able to form. The universe is supposed to be homogeneous and isotropic at large scales. What that means is that when you zoom out far enough, the universe should look the same in every direction. There shouldn't be any preferred direction or any particularly special location. Everything should average out to uniform smoothness. This principle, called the cosmological principle, has been a cornerstone of our understanding of the universe for nearly a century. It's supported by observations of the cosmic microwave background radiation, the afterglow of the Big Bang, which appears remarkably uniform across the entire sky. The existence of Quipu doesn't necessarily disprove the cosmological principle, but it does force cosmologists to think more carefully about what it means. At what scale does the universe become smooth? How large can structures be before they violate our assumptions? There's a theoretical limit on how large structures can be at any given age of the universe. Gravity can only pull things together so fast. The speed at which structure can grow is limited by fundamental physics. Quipu appears to push against this limit. It's so large that explaining how it formed within the 13.8 billion year history of the universe requires careful analysis. Several possibilities are being explored. Perhaps our models of structure formation need refinement. Perhaps dark matter behaves differently than we expect at very large scales. Perhaps the initial conditions in the early universe, the tiny density fluctuations that seeded all later structure, were different than we assumed. Or perhaps there's new physics at play that we haven't yet discovered. The honest answer is that we don't fully know. Quipu is a mystery, a challenge to our understanding, a reminder that the universe is larger and stranger than we imagined. The galaxy clusters that make up Quipu deserve closer attention because understanding the components helps us appreciate the whole. Galaxy clusters are the largest gravitationally bound structures in the universe. Unlike filaments and great walls, which are loose associations of galaxies flowing along the cosmic web, galaxy clusters are dense concentrations of galaxies held together by gravity. The galaxies within a cluster orbit a common center of mass, trapped by the cluster's gravitational pull. A typical galaxy cluster contains hundreds to thousands of galaxies, plus vast amounts of hot gas and dark matter. The gas between galaxies in a cluster can reach temperatures of 100 million degrees, so hot that it emits X-rays. This hot gas actually contains more mass than all the visible galaxies in the cluster combined. And the dark matter contains even more mass than the gas, typically about 5 to 6 times as much. When Fritz Zwicky studied the Coma cluster in the 1930s, he noticed that the galaxies were moving too fast to be held together by the visible matter alone. This was one of the first pieces of evidence for dark matter. The cluster's gravity was stronger than its visible mass could explain. Something invisible was adding to the gravitational pull. The clusters in Quipu range from modest groups containing a few hundred galaxies to massive concentrations containing thousands. They're connected by filaments of dark matter and hot gas, forming a network that spans 1.4 billion light-years. The gravitational influence of each cluster extends far beyond its visible boundaries, reaching out to interact with neighboring clusters and maintain the structural integrity of the whole system. When galaxy clusters collide, which happens when the filaments of the cosmic web bring them together, the results are among the most energetic events in the universe since the Big Bang. The galaxies themselves rarely hit each other directly because the spaces between galaxies are so vast. But the hot gas that fills each cluster does collide, creating shockwaves that heat the gas to even higher temperatures. These mergers can take billions of years to complete, during which time the clusters slowly merge into a single, larger structure. Within Quipu, some clusters may currently be in the process of merging. Others may have merged billions of years ago. Still, others may be approaching each other, destined to collide in the distant future. The structure is dynamic, evolving, changing over cosmic timescales. The voids between structures like Quipu are fascinating in their own right. Cosmic voids are the least dense regions of the universe. They're not completely empty. Even the emptiest voids contain some matter, a thin scattering of galaxies, clouds of gas, dark matter halos. But compared to the filaments and clusters, voids are practically vacuums. The average density in a void might be 1/10 or even 1/20th of the cosmic average. The largest known void, the giant void or Boötes void, is about 330 million light-years across. Within this enormous region, only about 60 galaxies have been found. That sounds like a lot until you realize that a similar volume elsewhere in the universe might contain 2,000 galaxies or more. What would it be like to exist inside a void? Imagine a civilization evolving on a planet inside the Boötes void. When they looked up at their night sky, they would see very few galaxies. Their own galaxy would be visible, a band of stars stretching across the darkness. But the distant glow of other galaxies would be much harder to detect. Their cosmic horizon would feel much closer, much more confining. They might conclude that their galaxy was alone in the universe, an island of matter in an infinite emptiness. The existence of voids is just as important for understanding the universe as the existence of filaments and walls. The voids represent the places where matter flowed away over billions of years, evacuating into the surrounding filaments and clusters. The voids and the filaments are two sides of the same coin. You can't have one without the other. The cosmic web is defined as much by its emptiness as by its fullness. Picture what it would be like to travel across Quipu. You board an impossible spacecraft, one that can accelerate instantly to the speed of light. You position yourself at one edge of Quipu and begin your crossing. The structure stretches before you. 1.4 billion light-years of galaxy clusters and filaments and hot gas and dark matter. For the first million years, you travel through relatively sparse regions. Quipu isn't uniformly dense. It has structure within structure. Occasionally, you pass a galaxy, a spiral of light containing billions of stars. But mostly there's emptiness, thin gas, invisible dark matter, the faint glow of the cosmic microwave background. After 10 million years, you encounter your first major galaxy cluster. You see hundreds of galaxies spread across millions of light years, embedded in a cloud of gas so hot it glows in X-rays. You pass through this cluster over the next few million years, watching galaxies drift past, each one a collection of hundreds of billions of stars. Then more relatively empty space. Filaments of matter stretch between clusters, thinner than the clusters themselves, but still containing galaxies and gas. You follow these filaments, watching the cosmic web unfold around you. After 100 million years, you've crossed less than a tenth of Quipu. Back on Earth, if Earth still exists, 100 million years have passed. The continents have shifted. Mountain ranges have risen and eroded. Entire groups of species have evolved and gone extinct. And you're still near the beginning of your journey. You continue, cluster after cluster, filament after filament. The structure seems endless. Each cluster you pass contains its own unique collection of galaxies, its own unique patterns of hot gas, its own unique history of formation and merger. You could spend millennia studying just one cluster and still not understand all its secrets. After 500 million years, you're about a third of the way across. On Earth, complex multicellular life might be evolving for the first time. Or perhaps life has gone extinct and started over. Or perhaps the planet has been hit by an asteroid, or frozen in a snowball Earth event, or baked by volcanic eruptions. 500 million years is enough time for almost anything to happen. After 1 billion years, you're approaching the far side of Quipu. Our star has changed noticeably. It's brighter than it was when you left, burning through its hydrogen fuel. Earth's oceans may be beginning to evaporate. The conditions that allowed human life to flourish are fading. Finally, after 1.4 billion years, you emerge from the far side of Quipu. Behind you lies the largest known structure in the universe. Billions of galaxies, trillions upon trillions of stars, countless worlds. Ahead lies whatever lies beyond. More cosmic web, more filaments and voids, more structures waiting to be discovered. The journey I just described is impossible. Nothing with mass can travel at the speed of light. And even if you could somehow achieve light speed, 1.4 billion years is an unimaginably long time. But the thought experiment helps illustrate what we mean when we say something is 1.4 billion light-years across. Zooming out one more time, consider the observable universe as a whole. The observable universe is a sphere centered on Earth with a radius of about 46.5 billion light-years. You might wonder how that's possible if the universe is only 13.8 billion years old. The answer is that space has been expanding while the light was traveling toward us. When we look at a galaxy whose light took 13 billion years to reach us, that galaxy has been moving away from us due to cosmic expansion the entire time. By now, that galaxy is much farther away than 13 billion light-years. Within this observable sphere, there are approximately 2 trillion galaxies. Each galaxy contains billions or hundreds of billions of stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. And we now know that most stars have planets. The number of planets in the observable universe is probably similar to or even larger than the number of stars. And here's the thing. The observable universe is not the entire universe. The observable universe is just the part we can see, limited by the speed of light and the age of the cosmos. There's almost certainly more universe beyond our cosmic horizon, regions of space so far away that light from them hasn't had time to reach us yet, and never will. How much more universe is out there? We don't know. Some theories suggest the universe might be infinite, stretching endlessly in all directions. Other theories suggest it might be finite, but unbounded, like the surface of a sphere. The honest answer is that we have no way of knowing. This means Quipu, as large as it is, might be small compared to structures beyond our cosmic horizon. There might be cosmic webs spanning hundreds of billions of light-years out there. We'll never know. The universe is expanding, and that expansion is accelerating. Dark energy is pushing the universe apart at an ever-increasing rate. Distant galaxies are receding from us as space expands between us and them. The farther away a galaxy is, the faster it's receding. For galaxies that are far enough away, space between us and them is expanding faster than light can travel through it. This doesn't violate the cosmic speed limit because the galaxies themselves aren't moving faster than light through space. They're essentially stationary in their local space. But the space itself is expanding so rapidly that the distance between us grows faster than light could traverse it. This has implications for the future of structures like Quipu. As the universe continues to expand, the growth of structure will slow down. Dark energy will eventually win its battle against gravity. Galaxy clusters that haven't merged yet never will. Filaments will stop growing. The cosmic web will freeze into its final configuration. In the far future, perhaps tens of billions of years from now, Quipu will be more isolated. The connections between its clusters may thin or break. The structure will persist, but will be surrounded by an ever-expanding void as the rest of the universe recedes beyond our ability to observe. How do astronomers actually detect structures like Quipu? Finding something 1.4 billion light-years across isn't easy. We can't just point a telescope at the sky and see Quipu directly. It's too big, too far away, and spread across too much of the sky. To find structures this large, astronomers use multiple techniques. Redshift surveys are the workhorse of large-scale structure studies. When a galaxy is moving away from us, the light it emits gets stretched out. The wavelengths become longer, shifting toward the red end of the spectrum. This is called redshift. The amount of redshift tells us how fast a galaxy is receding. And because recession speed is related to distance in an expanding universe, redshift tells us how far away a galaxy is. By measuring the redshifts of millions of galaxies, astronomers can build three-dimensional maps of the universe. They plot each galaxy's position in the sky and its distance from us, creating a cosmic atlas that shows where galaxies are distributed throughout space. X-ray observations are particularly important for finding structures like Quipu. Galaxy clusters contain vast amounts of hot gas that emits X-rays. By mapping X-ray emissions across the sky, astronomers can identify clusters and trace the connections between them. This is how Quipu was discovered, using data from the Rosat satellite combined with other surveys. The Sloan Digital Sky Survey has been running since 2000 and has produced some of the most detailed three-dimensional maps of the universe ever made. The Dark Energy Spectroscopic Instrument is currently extending these maps to fainter and more distant galaxies. Weak gravitational lensing is another powerful technique. When light from distant galaxies passes near massive structures, it gets bent slightly by gravity. By measuring these distortions statistically across millions of galaxies, astronomers can map the distribution of mass in the universe, including dark matter that doesn't emit light. The cosmic microwave background provides information about the universe when it was only 380,000 years old. Small temperature variations in the CMB correspond to small density variations in the early universe. These were the seeds of all later structure. Numerical simulations are essential for understanding how structure forms. Cosmologists use supercomputers to simulate the evolution of the universe from shortly after the Big Bang to the present day. They set up initial conditions matching CMB observations, include the effects of gravity, dark matter, dark energy, and gas physics, then let the simulation run. The results show filaments and voids and walls forming over billions of years, matching observations remarkably well. These simulations help us understand what's normal and what's unusual. When we discover a structure like Quipu, we can check whether similar structures appear in simulations. If they do, we can study how they formed. If they don't, we know something is missing from our models. The future holds remarkable possibilities for our understanding of these massive structures. New telescopes and surveys are coming online that will map the universe with unprecedented precision. These instruments will reveal details of the cosmic web that previous generations of astronomers could only dream of seeing. The Vera C. Rubin Observatory in Chile will begin operations soon and will image the entire visible sky every few nights, cataloging billions of objects. The European Space Agency's Euclid mission, launched in 2023, is mapping the geometry of the dark universe, studying how dark matter and dark energy have shaped the cosmic web over billions of years. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will have a field of view 100 times larger than Hubble's. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the world's largest radio telescope. One of its key science goals is to map the distribution of hydrogen gas throughout the cosmic web. By mapping this gas, it will reveal the structure of the cosmic web in unprecedented detail. The Laser Interferometer Space Antenna, or LISA, is a planned, space-based gravitational wave observatory. Unlike ground-based detectors like LIGO, LISA will be sensitive to much lower frequencies. This means it can detect gravitational waves from supermassive black holes at the centers of galaxies, including black holes in the process of merging when galaxy clusters collide. These and other future instruments will find new structures, test our theories, and raise new questions. They might discover structures even larger than Quipu. Or they might confirm that Quipu is close to the maximum size that structures can achieve. Consider the stars we can see with our naked eyes and what their light tells us about distance and time. When you look up at the night sky, you're not seeing stars as they are right now. You're seeing light that has traveled for years or centuries to reach your eyes. Distance and time become inseparable. You cannot separate where something is from when you're seeing it. Sirius, the brightest star in the night sky, is 8.6 light-years away. When you look at Sirius tonight, you're seeing light that left that star 8.6 years ago. If you're 20 years old, you're seeing Sirius as it was when you were about 11. Vega is another bright star, about 25 light-years away. If you're 25 years old and you look at Vega tonight, you're seeing light that left that star the year you were born. When that light began its journey toward Earth, you hadn't been born yet. Betelgeuse, the red supergiant in the constellation Orion, is about 550 light-years away. The light you see from Betelgeuse tonight started its journey toward Earth in the year 1474 during the Italian Renaissance. Leonardo da Vinci was 22 years old. Michelangelo was about to be born. The modern world as we know it didn't exist yet. Betelgeuse is particularly interesting because it's a massive star nearing the end of its life. At some point in the relatively near future, astronomically speaking, within the next 100,000 years or so, Betelgeuse will explode as a supernova. When it does, it will briefly shine as bright as the full moon in our sky, visible even during the day. But here's the thing. Betelgeuse might have already exploded. The explosion might have happened centuries ago, but we wouldn't know yet. The light from that explosion would still be traveling toward us through space, taking 550 years to make the journey. Polaris, the North Star, is about 445 light-years away. When its current light began traveling toward us, Shakespeare had just begun writing his plays. The United States wouldn't exist for another 180 years. Every star you see in the night sky is a window into the past. You're not seeing the universe as it is. You're seeing the universe as it was, the information traveling across the light years to reach you tonight. This has profound implications for how we understand structures like Quipu. When we observe Quipu, we're seeing different parts of it at different times. The near edge, 425 million light-years away, appears as it was 425 million years ago. The far edge, 800 million light-years away, appears as it was 800 million years ago. We're not seeing Quipu as a snapshot frozen in a single moment. We're seeing it smeared across 375 million years of cosmic history. This means we can actually study how structures evolve by looking at different distances. Looking farther away is like looking back in time. When we compare nearby galaxy clusters to distant galaxy clusters, we're comparing the universe today to the universe billions of years ago. This is how we know that galaxy clusters grow over time, that filaments stretch and thin, that the cosmic web evolves. You might be wondering why any of this matters. Why should we care about structures billions of light years away? There are practical reasons worth considering. Understanding the cosmic web helps us understand galaxy formation and evolution. It informs our theories of dark matter and dark energy. It tests our models of cosmology and fundamental physics. Scientific knowledge builds on itself. Understanding the largest structures helps us understand everything else. But beyond the practical, there's something deeply human about contemplating the scale of the universe. We are curious creatures by nature. We want to know where we came from, where we are, and where we might be going. We want to understand our place in the grand scheme of things. And there's perspective to consider as well. In our daily lives, we get caught up in small concerns, traffic jams, work deadlines, interpersonal dramas. These things feel important, and in their way they are genuinely important. But stepping back to contemplate structures spanning billions of light years can provide a different kind of importance. A reminder that we're part of something much larger. This brings us to the question of what these cosmic structures mean for the possibility of life elsewhere in the universe. Given the vast number of stars and planets, given that the universe is 13.8 billion years old, given that life arose on Earth relatively quickly after conditions became suitable, it seems likely that life should exist elsewhere. And yet, we've never detected any signs of alien civilizations. No radio signals, no laser pulses, no megastructures, nothing. The universe appears to be silent. The vast distances measured in light years might be part of the answer. The distances between stars are so enormous that they present barriers to communication and travel that might simply be insurmountable. Our radio signals have been leaking into space for about a century now. These signals travel at light speed, spreading outward in an expanding sphere. They've now reached all stars within about 100 light-years of Earth. That sounds like a lot, but the Milky Way galaxy is 100,000 light-years across. Our signals have covered a tiny fraction of the galaxy. Even if there's an advanced technological civilization on a planet within Quipu, even if they've been broadcasting signals for millions of years, those signals would take hundreds of millions of years to reach us. And our response would take hundreds of millions of years to reach them. Meaningful communication across these distances might simply be impossible. This creates a picture of a universe that might be full of life, but where that life is forever isolated by the vast distances of space. Each civilization develops alone, asks its questions alone, makes its discoveries alone, and eventually dies alone, never knowing if anyone else was out there. There's something melancholy about this. We've evolved as social creatures. Connection with others is fundamental to who we are. The idea of being surrounded by others but forever unable to reach them is profoundly isolating. But there's also something beautiful about it. It means every civilization that does arise is precious. If we're alone, or effectively alone, then what we do here matters enormously. We might be the only consciousness in our region of space. The thoughts we think, the art we create, the science we discover, the love we feel, all of it is unique to us. There's something profound about what the cosmic web tells us about the nature of reality itself. The universe is not a random scattering of particles. It has structure at every scale. Quarks combine into protons and neutrons. Protons and neutrons combine into atoms. Atoms combine into molecules. Molecules combine into cells. Cells combine into organisms. Organisms form ecosystems. Stars form galaxies. Galaxies form clusters. Clusters form superclusters. Superclusters align along filaments that stretch across billions of light years. At each scale, new properties emerge that couldn't be predicted from the scale below. A single atom doesn't have temperature, but a collection of atoms does. A single cell doesn't have consciousness, but a collection of cells, organized in the right way, might. A single galaxy doesn't have a cosmic web, but a collection of galaxies interacting gravitationally over billions of years, produces one. This hierarchy of structure suggests something deep about reality. The universe isn't just a collection of parts, it's a system of systems, organized at multiple scales, each scale with its own patterns and behaviors. Quipu is the largest known example of this hierarchical organization. It's the universe's skeleton at its grandest scale, the framework on which everything else hangs. When we map its structure, we're mapping the deepest level of organization in the physical world. But who knows? Perhaps there are structures larger still. Perhaps the observable universe is just one cell in an infinite cosmic organism. Perhaps patterns we can't see extend beyond our cosmic horizon, organizing matter at scales we can't imagine. This is the nature of scientific inquiry. Every answer leads to more questions. Every discovery reveals more mysteries. We'll never reach the end of understanding. The universe is too large, too complex, too strange. But that's what makes the journey worthwhile. Our own cosmic neighborhood has its own dramatic future worth considering. The Milky Way and Andromeda are moving toward each other. Recent studies have refined our understanding of this approach, with updated velocity data suggesting the situation is more complex than once thought. The two galaxies may experience a close encounter in about 4 to 5 billion years, though there's now estimated to be about a 50% chance they might not fully merge within the next 10 billion years. If a merger does occur, it will be a spectacular but slow event. The galaxies will interact gravitationally, distorting each other's shapes, triggering waves of star formation, eventually settling into a single larger galaxy, sometimes called Milkomeda. The collision won't be violent in the usual sense. Stars almost never collide directly because the distances between them are so vast. It would be more like two swarms of bees passing through each other. But none of that affects our understanding of Quipu. Our local group, the Milky Way and Andromeda, and all the smaller galaxies around them, is just one tiny knot in the cosmic web. Whatever happens here is happening in countless other places throughout the universe. Time plays a crucial role in understanding these structures. The cosmic web wasn't always there. It had to form. Understanding how it grew tells us something profound about cosmic evolution. In the very early universe, right after the Big Bang, matter was distributed almost perfectly uniformly. No stars, no galaxies, no filaments or walls. Just a nearly featureless glow of hot plasma cooling rapidly as space expanded. But hidden within that apparent smoothness were tiny variations in density, seeded by quantum fluctuations during inflation. These variations were incredibly small, perhaps 1 part in 100,000, but they were enough. Gravity began to work on these tiny variations. The slightly denser regions attracted matter from their surroundings, becoming denser still. The less dense regions lost matter to their neighbors, becoming even emptier. Over millions and then billions of years, the contrast between dense and empty regions grew. The first structures to form were small. Dark matter collected into halos, perhaps a few thousand light-years across. Within these halos, ordinary matter cooled and condensed, forming the first stars. These early stars lived fast and died young, exploding as supernovae. The first galaxies assembled from these building blocks. Small halos merged to form larger ones. Galaxies began to cluster together. Clusters aligned along filaments. The cosmic web emerged. This process took billions of years. Quipu, as we see it today, is the product of nearly 13 billion years of gravitational evolution. It's a snapshot of a process that's still ongoing. Galaxies, are still falling into clusters. Filaments are still growing, though more slowly now as dark energy's influence increases. But the growth of structure is slowing down. Dark energy is accelerating the expansion of the universe, stretching space between galaxies faster and faster. This expansion works against gravity, making it harder for matter to clump together. Eventually, dark energy will win. The growth of structure will stop. This hasn't happened yet. We live in a transitional era. In the far future, the universe will look very different. Quipu will be more isolated. The connections between its clusters may thin or break. The cosmic web will be sparser, more fragmented. Over immense timescales, even the stars will die. Our star will exhaust its fuel in about 5 billion years, though Earth's habitability will decline much sooner, perhaps within 1 to 2 billion years, as the star gradually brightens. The last stars in the universe, small red dwarfs, will burn for trillions of years, but eventually they too will fade. Even black holes won't last forever. Through Hawking radiation, black holes slowly evaporate. The largest black holes might take 10 to the power of 100 years to evaporate, but still, eventually, they'll be gone. In the very far future, the universe will be a cold, dark, nearly empty void. The cosmic web will be a distant memory. The largest structures ever built will have been dismantled by the relentless expansion of space. But that's trillions of years away. For now, the universe is full of light and structure and wonder. Here's what strikes me most when I think about perspective. When we contemplate Quipu, we're confronting the limits of human comprehension. Our brains evolved for survival on the African savanna. We're good at tracking predators, finding food, navigating familiar terrain. We're not designed to comprehend structures billions of light years across. The numbers are simply too large. They exceed our cognitive grasp. And yet, we can understand them mathematically. We can write down equations that describe how structures form. We can simulate the cosmic web on supercomputers. We can make predictions and test them against observations. Mathematics extends our reach far beyond what our intuition can grasp. From a cosmic perspective, you're insignificant. Your life is a brief flicker, perhaps 80 or 90 years in a universe that's 13.8 billion years old and will continue for trillions of years more. You exist for the blink of an eye on a tiny planet orbiting an ordinary star. But you're also remarkable. You're made of atoms forged in the hearts of stars that died billions of years ago. Their matter was scattered across space and eventually recycled into new stars and planets and ultimately into you. You're literally made of stardust, the product of cosmic processes that have been operating for billions of years. And you can understand, you can contemplate structures 1.4 billion light years across. You can grasp, at least mathematically, the scale of the universe that created you. You're the universe's way of knowing itself, at least in this tiny corner of space. Quipu is 1.4 billion light years across. It contains 68 galaxy clusters, trillions of stars, countless worlds. It's the largest known coherent structure in the observable universe. It took billions of years to form and will persist for billions more. And you know about it. You've spent time learning about it. You've contemplated distances that dwarf anything in human experience. That's an achievement. A small one in cosmic terms, but real nonetheless. The next time you look up at the stars on a clear night, remember what you've learned tonight. Those points of light are not just stars. They're part of a galaxy, which is part of a cluster, which is part of a supercluster, which is part of the cosmic web stretching across billions of light years. You're connected to all of it, made of the same atoms, subject to the same physics, part of the same cosmic story. Every star has a story. Some are young, just forming from collapsing clouds of gas and dust. Some are middle-aged, steadily burning hydrogen in their cores. Some are old, approaching the end of their lives. And all of them are connected by the cosmic web, by gravity, by the fact that they're all made of the same stuff, atoms forged in earlier generations of stars. The universe is a sparse place, with tiny islands of light separated by enormous oceans of darkness. And yet, those islands are connected by light, connected by gravity, connected by history. Thank you for taking this journey with me. If you found this exploration valuable, please consider liking and subscribing. And remember, the next time you look up at the stars, you're seeing just a tiny fraction of a universe far larger and far stranger than anyone imagined. We're all made of stardust, part of a cosmic web that spans the observable universe. Small in the grand scheme of things, but infinitely curious, infinitely capable of wonder. Sleep well, and may you never stop asking questions about the universe we call home. But before I let you drift off, there's more to explore about these cosmic structures. We can go deeper into the science and the wonder of what we've discovered. Galaxy clusters are the building blocks of structures like Quipu, and understanding them helps us appreciate the whole. A galaxy cluster is like a city made of galaxies. Just as a city contains thousands of buildings connected by streets and infrastructure, a galaxy cluster contains hundreds or thousands of galaxies connected by gravity and surrounded by shared resources. In a city, the shared resources might be water systems, electrical grids, and transportation networks. In a galaxy cluster, the shared resources are vast reservoirs of hot gas and invisible scaffolding of dark matter. The hot gas in a galaxy cluster is called the intracluster medium. This gas didn't come from the galaxies themselves. Most of it was never part of any galaxy. It's primordial gas, hydrogen and helium left over from the Big Bang that fell into the gravitational well of the cluster and was heated by compression as it fell. When you compress gas, it heats up. When you compress gas, falling into a gravitational field as deep as a galaxy cluster's, it heats up to temperatures of tens of millions of degrees. This gas is so hot that it glows in X-rays. When astronomers point X-ray telescopes at galaxy clusters, they see a diffuse glow filling the space between galaxies. This glow reveals the shape and extent of the cluster, showing structure that would be invisible in ordinary visible light. The total mass of hot gas in a typical galaxy cluster is actually greater than the total mass of all the galaxies in the cluster combined. If you added up all the stars in all the galaxies in a cluster, and then weighed the hot gas between those galaxies, the gas would win by a factor of 5 or 6. The galaxies themselves, as impressive as they are almost like impurities floating in a sea of hot plasma. But even the hot gas is not the dominant component. Dark matter is. Dark matter makes up about 85% of the total mass of a typical galaxy cluster. It provides the gravitational framework that holds everything else together. Without dark matter, the hot gas would disperse into space. The galaxies would drift apart. The cluster would fall apart. Dark matter doesn't interact with light, which is why we call it dark. It doesn't emit light, absorb light, or reflect light. The only way we know it's there is through its gravitational effects. We see galaxies moving too fast to be held by visible matter alone. We see light from distant sources bent by invisible mass. We see the hot gas held in shapes that require more gravity than we can account for with ordinary matter. The existence of dark matter was first inferred from observations of galaxy clusters in the 1930s, when Fritz Zwicky noticed the velocity dispersion problem I mentioned earlier. Since then, evidence for dark matter has accumulated from dozens of different sources. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, the formation of large-scale structure. All of these observations point to the same conclusion. There is far more mass in the universe than we can see, and it's not made of atoms. We still don't know what dark matter actually is. The leading candidates are weakly interacting massive particles, or WIMPs, hypothetical particles that interact only through gravity and possibly the weak nuclear force. Decades of experiments have searched for WIMPs directly, using detectors deep underground to shield them from cosmic rays. So far, no definitive detection has been made. Other candidates include actions, extremely light particles proposed to solve a different problem in particle physics. Primordial black holes. Black holes formed in the early universe that might account for some or all of the dark matter. Sterile neutrinos, hypothetical particles heavier than ordinary neutrinos. The honest answer is that we don't know. Dark matter remains one of the deepest mysteries in physics. When galaxy clusters collide, the results are among the most spectacular events in the universe. Galaxy clusters don't sit still. They move through space, following the flows of the cosmic web, falling toward denser regions, approaching other clusters that happen to lie in their path. When two galaxy clusters approach each other closely, they begin to interact gravitationally, falling toward each other until they merge. The merger of two galaxy clusters takes about 1 billion years to complete. During this time, the clusters pass through each other, swing around, pass through again, and gradually settle into a single larger cluster. It's like two swarms of bees merging, except the swarms are millions of light years across and contain thousands of galaxies. When the clusters first collide, their galaxies pass through each other almost without interaction. The spaces between galaxies are so vast that direct collisions between galaxies are extremely rare. A typical galaxy might be 100,000 light-years across, but the average distance between galaxies in a cluster might be millions of light-years. The galaxies slip past each other like ghosts, but the hot gas is a different story. The intra-cluster medium of each cluster occupies the entire volume of the cluster. When the clusters collide, their gas collides too. This creates tremendous shock waves that heat the gas to even higher temperatures, sometimes exceeding 100 million degrees. These shock waves can be seen in X-ray observations as bright arcs and edges in the gas distribution. The collision also affects the dark matter, but not in the same way it affects the gas. Dark matter is collisionless. It doesn't interact with itself, except through gravity. So when the clusters merge, their dark matter halos pass through each other just like the galaxies do. The gas, however, is slowed by the collision and it lags behind. This separation between dark matter and gas has been directly observed in several merging clusters. The most famous example is the Bullet cluster, where astronomers have mapped both the distribution of hot gas using X-rays and the distribution of total mass using gravitational lensing. The maps show that the mass is centered on the galaxies, not on the gas. This is strong evidence that most of the mass is dark matter, which stayed with the galaxies rather than ordinary matter, which collided and was left behind. The Bullet cluster is about 3.8 billion light-years away. We're seeing it as it was 3.8 billion years ago, when Earth's sun was already shining, but the solar system was only about 700 million years old. The merger that created the Bullet Cluster was already ancient history by the time life began on Earth. Within Quipu, multiple cluster mergers may be occurring right now. Or rather, they may have occurred hundreds of millions of years ago, and the light showing us those mergers is still on its way to Earth. The structure is dynamic, evolving, changing in ways we can observe by comparing clusters at different distances. Some specific clusters illustrate what structures like Quipu contain. These are the laboratories where we study cosmic evolution. The Virgo cluster, located about 54 million light-years away, is the nearest large galaxy cluster to us. It contains about 1,300 to 2,000 galaxies, dominated by several giant elliptical galaxies near the center. The largest of these is M87, a massive elliptical galaxy with a famous supermassive black hole that was the first black hole ever directly imaged. The Virgo cluster is the heart of our local region of the cosmic web. The Milky Way, along with the rest of the local group, is slowly falling toward the Virgo cluster at about 620 miles per second. We'll never actually reach it in any meaningful time frame because the expansion of the universe is carrying the cluster away from us at a similar rate. But the gravitational influence of the Virgo cluster shapes the motions of galaxies for hundreds of millions of light-years around it. The Coma cluster, about 321 million light-years away, is one of the richest and most studied galaxy clusters. It contains over 1,000 large galaxies and probably tens of thousands of smaller dwarf galaxies. The cluster is named after the constellation Coma Berenices, where it appears in our sky. The Coma cluster was where Fritz Zwicky first detected evidence for dark matter in the 1930s. He measured the velocities of galaxies in the cluster and found they were moving much faster than they should be based on the visible mass of the cluster. Either the laws of physics were wrong, or there was more mass present than met the eye. We now know that Zwicky was right about the extra mass. The Perseus cluster, about 240 million light-years away, is one of the brightest X-ray sources in the sky outside our own galaxy. It contains a particularly spectacular active galactic nucleus at its center, where the supermassive black hole in the central galaxy is shooting jets of material out into the surrounding gas. These jets carve enormous bubbles in the intracluster medium, creating cavities that can be seen in X-ray images. The sound waves generated by these bubbles rippling through the hot gas have been detected. The note they produce is roughly a B flat, about 57 octaves below middle C. This is the deepest sound ever detected, with a period of about 10 million years per oscillation. The internal structure of Quipu reveals even more complexity. The 68 galaxy clusters that make up Quipu aren't randomly distributed. They're arranged along preferred directions, connected by filaments of dark matter and hot gas that stretch between them like threads connecting beads on a necklace. Some clusters are more massive than others. Some are isolated, connected to only one or two neighbors. Others are intersection points, connected to multiple filaments leading in different directions. The astronomers who discovered Quipu identified it by looking for patterns in the X-ray emission from galaxy clusters. They noticed that certain clusters, despite being separated by hundreds of millions of light-years, were connected by bridges of faint X-ray emission. These bridges indicated hot gas stretching between the clusters, gas that could only be present if the clusters were physically connected rather than merely appearing close together by chance. The mass distribution within Quipu is not uniform. The central regions are denser, containing more massive clusters with shorter connections between them. The outer regions are more sparse, with smaller clusters and longer filaments. This is typical of cosmic structure at all scales. Dense cores surrounded by less dense outskirts, a consequence of how gravity assembles matter over time. If you could somehow see Quipu from the outside, looking at the entire structure at once, it might resemble a complex root system or a network of blood vessels. Dense nodes connected by thinner channels, with the whole thing embedded in a sea of even more diffuse gas and dark matter. But we can't see it from the outside. We're inside the observable universe, seeing Quipu from billions of light years away. And we're not even seeing it as it is now, but as it was hundreds of millions of years ago. The implications of Quipu's discovery for our understanding of cosmic evolution are significant. The existence of a structure this large, this early in cosmic history, provides important constraints on our models of how the universe evolved. Quipu is about 800 million light-years away at its most distant point, which means the light we're seeing left when the universe was about 13 billion years old. The universe had had 13 billion years to build this structure, which sounds like a long time until you realize how much assembly was required. Each of the 68 clusters in Quipu took billions of years to form. The dark matter halos that anchor each cluster began as small density perturbations in the early universe. These perturbations grew over time, attracting more matter, merging with other halos, eventually becoming massive enough to be called galaxy clusters. This process is well understood and matches our simulations. But the clusters also had to find each other. They had to be arranged in space in such a way that they could be connected by filaments, that matter could flow between them, that they could act as a coherent structure rather than isolated objects. This requires the initial conditions in the early universe to have been just right. The density perturbations that seeded each cluster had to be positioned correctly relative to each other, separated by the right distances, embedded in the right larger-scale density field. Our current models of cosmology predict that structures like Quipu should exist, but they also predict that they should be rare. The fact that we found one within the relatively small volume of the observable universe that we've mapped so far suggests either that we got lucky, or that structures like this are more common than we expected, or that there's something about structure formation we don't fully understand. This is how science works. We make observations. We compare them to predictions. When the observations match, we gain confidence in our theories. When they don't match, or when they push against the edges of what our theories allow, we learn something new. The cosmic microwave background connects directly to structures like Quipu. The cosmic microwave background, or CMB, is the oldest light in the universe. It was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. Before that moment, the universe was a hot plasma of electrons and atomic nuclei. Light couldn't travel freely because it was constantly scattered by free electrons. The universe was opaque. When atoms formed, the electrons were captured by nuclei, and the universe became transparent. Light could suddenly travel freely. The photons that were released at that moment have been traveling ever since, crossing the universe in all directions. We detect them today as a faint glow of microwave radiation coming from every part of the sky. The CMB is remarkably uniform. Whichever direction you look, it has almost exactly the same temperature, about 2.7 degrees above absolute zero. This uniformity tells us that the universe was very smooth shortly after the Big Bang. All parts of the universe started from almost the same conditions, but not exactly the same. When we look at the CMB very carefully, we see tiny variations in temperature, about 1 part in 100,000. These variations map out the density fluctuations in the early universe. Slightly denser regions appear slightly warmer. Slightly less dense regions appear slightly cooler. These tiny variations are the seeds of all the structure we see today. Over 13.8 billion years, gravity amplified these fluctuations. The slightly denser regions became the galaxy clusters and filaments of the cosmic web. The slightly less dense regions became the voids. The pattern we see in the CMB is a direct ancestor of the pattern we see in the distribution of galaxies today. Astronomers have traced this connection in detail. They can take the map of CMB fluctuations, feed it into computer simulations of cosmic evolution, and predict what the universe should look like today. The predictions match observations remarkably well. The same statistical patterns appear in both. The cosmic web is the grown-up version of the baby universe captured in the CMB. Quipu itself is too large and too nearby to be directly connected to any specific feature in the CMB. The fluctuations in the CMB are on much smaller angular scales, but the statistics of the CMB tell us how common structures like Quipu should be, and this is where the tension arises. Structures this large are expected to be rare, appearing only in large volumes of space. Finding Quipu relatively nearby suggests either good fortune or incomplete theory. What lies beyond Quipu? This question takes us to the edge of what we can know. The observable universe is vast, but it's not infinite. It has a definite size, about 93 billion light-years in diameter. Beyond the edge of the observable universe, space continues, but light from those regions hasn't had time to reach us. And due to the accelerating expansion of space, light from sufficiently distant regions never will reach us. Those regions are beyond our cosmic horizon forever. What exists beyond the horizon? Almost certainly more of the same. More galaxies, more clusters, more filaments and voids. The universe is expected to be homogeneous on large scales, meaning the region beyond our horizon should look statistically similar to the region within. There should be structures comparable to Quipu scattered throughout, each one the local largest structure in its region of space. But we have no way to know for sure. We can never observe those regions. We can never send signals to them or receive signals from them. They are causally disconnected from us. For all practical purposes, they might as well not exist. Some cosmologists have speculated about what lies beyond. If the universe is infinite, as some models suggest, then everything that can happen will happen somewhere. There should be other solar systems identical to ours. Other Earths. Other copies of you, reading or hearing these exact words. This idea, called the Level 1 multiverse, is a logical consequence of an infinite universe, but it's impossible to verify. Other models suggest the universe might be finite, but unbounded, like the surface of a sphere. You could travel in any direction forever without reaching an edge, but the total volume would be finite. In this case, structures larger than the observable universe wouldn't exist, but we'd never know because we can only see a fraction of the whole. The honest answer is that we don't know. The universe keeps its largest secrets hidden behind our cosmic horizon. The practical challenges of studying structures as large as Quipu are formidable. The first challenge is simply seeing it. Quipu spans a large fraction of the sky as seen from Earth. Its 68 clusters are scattered across a region that might cover thousands of square degrees. To map it completely, you need surveys that cover large areas of the sky with sensitivity to faint X-ray emission, or the weak gravitational lensing signals that reveal the underlying mass distribution. The ROSAT satellite, which provided much of the data used to discover Quipu, was an X-ray telescope that operated in the 1990s. It surveyed the entire sky in X-rays, cataloging thousands of galaxy clusters. But its sensitivity was limited by the technology of its time. Many of the fainter clusters and connecting filaments in Quipu were only hinted at in ROSAT data, not definitively detected. Modern X-ray telescopes like Chandra and XMM Newton are more sensitive, but they have much smaller fields of view. They can study individual clusters in exquisite detail. But mapping an entire structure like Quipu would take thousands of individual observations, each pointed at a different part of the sky. The E-Rosetta telescope, launched in 2019, offers the best of both worlds. It's surveying the entire sky in X-rays, with sensitivity far exceeding ROSAT. Its data is revealing the cosmic web in unprecedented detail, finding clusters and filaments that were invisible to previous instruments. The discovery of Quipu relied partly on E-Rosetta data combined with older surveys. Optical surveys are also crucial. The Sloan Digital Sky Survey has mapped the positions and redshifts of millions of galaxies, revealing the three-dimensional structure of the cosmic web out to billions of light-years. The Dark Energy Survey and upcoming Vera Rubin Observatory Survey will extend this mapping to fainter galaxies and larger volumes. Gravitational lensing surveys provide yet another view. By measuring the tiny distortions in the shapes of distant galaxies caused by intervening mass, astronomers can map the distribution of dark matter directly. This reveals structure that would be invisible in light or X-rays. Combining all these observations is how astronomers piece together the existence and properties of structures like Quipu. No single technique is sufficient. Only by integrating data from multiple sources can we see the full picture. The second challenge is understanding what we're seeing. When we observe Quipu, we're not seeing it as a snapshot at a single moment in time. Different parts of the structure are at different distances from us, so we're seeing them as they were at different times in cosmic history. The nearest clusters in Quipu are about 425 million light-years away. The most distant are about 800 million light-years away. The difference is 375 million years of cosmic evolution. During that time, clusters grew larger, accumulated more mass, merged with neighbors. The structure changed. What we see is not Quipu as it is now, or Quipu as it was at some specific moment, but a smeared image of Quipu extending across 375 million years of history. It's as if you took a photograph of a city, but different buildings in the photograph were captured at different times, some showing the city as it was centuries ago, others showing it as it was decades ago. Untangling this is challenging. Astronomers must use models of how structures evolve to interpret what they observe. They must ask, if this cluster appears this way and is at this distance, how might it have looked earlier, or how might it look later? They must stitch together observations from different distances into a coherent picture of what the structure actually is. The third challenge is statistical. The universe is a random place, in the sense that the specific arrangement of matter depends on random fluctuations in the early universe. Different regions of the universe look different. Some regions, by chance, have more structure, others have less. Is Quipu unusual? Is it a rare fluctuation, a once-in-a-trillion chance configuration that happened to appear within our observable volume? Or is it typical, one of many similar structures scattered throughout the universe that we happen to have detected? Answering this question requires comparing observations to simulations. Cosmologists run large simulations of cosmic evolution, starting from random initial conditions drawn from the same statistical distribution as the real universe. They then look at the simulated universes and ask how often structures like Quipu appear. If structures like Quipu are common in simulations, then our theories are working. If they're rare or absent, then something is wrong with our assumptions. Current simulations suggest that structures comparable to Quipu should exist, but not in great abundance. Finding one within the volume we've mapped is not impossible, but it does suggest we may have gotten somewhat lucky. Or it suggests that our simulations aren't quite capturing the full range of what the universe can produce. The formation history of a structure like Quipu spans billions of years. Go back 13.8 billion years to shortly after the Big Bang. The universe is a hot, dense plasma expanding rapidly. Matter is distributed almost uniformly, but not quite. Tiny variations in density, seeded by quantum fluctuations during inflation, create a subtle pattern of slightly denser and slightly less dense regions. As the universe expands and cools, these variations begin to grow. Gravity pulls matter toward the denser regions. The denser regions become denser still. The less dense regions become emptier. After about 100 million years, the first stars begin to form in the densest regions. Small halos of dark matter containing just enough ordinary matter to collapse and ignite nuclear fusion. These first stars are very different from stars today. They're massive, hundreds of times the mass of our own star. They burn hot and fast, living only a few million years before exploding as supernovae. Their explosions spread the first heavy elements, carbon, oxygen, iron, throughout the surrounding gas. After about 200 million years, the first galaxies begin to assemble. Small halos merge into larger ones. Stars form in increasingly large groups. The universe transitions from a sea of isolated first stars to a network of small, irregular galaxies. As hundreds of millions of years pass, the galaxies grow. They merge with each other, building up mass. The largest halos attract more matter, becoming dominant in their regions. Galaxy groups form, collections of dozens of galaxies bound together by gravity. After about 1 billion years, the first true galaxy clusters begin to appear. These are the largest gravitationally bound structures, containing hundreds or thousands of galaxies, surrounded by vast halos of dark matter and filled with hot intra-cluster gas. The clusters don't form in isolation. They form along the filaments of the cosmic web, at the intersections where multiple filaments meet. Matter flows along the filaments, feeding the clusters, making them grow over time. As billions of years pass, the clusters grow larger. Some merge with each other, combining into even more massive structures. The filaments connecting them stretch as the universe expands, but they remain intact, continuing to channel matter toward the clusters. By the time the universe is 13 billion years old, structures like Quipu have assembled. Dozens of clusters connected by filaments, forming a network that spans over 1 billion light years. The growth is slowing now, as dark energy begins to dominate the universe's expansion, but the structure is largely in place. And 800 million years later, the light from these structures begins to reach Earth. We point our telescopes at the sky and see the network of clusters and filaments. We name it Quipu. We try to understand how it formed and what it tells us about the universe. Some common misconceptions about cosmic structures deserve attention. First, people sometimes think that galaxy clusters and cosmic structures are moving through space at high speeds, racing away from each other due to some initial explosive event. This isn't quite right. The galaxies within a cluster do move, orbiting the cluster's center of mass at speeds of hundreds or thousands of miles per second. But the clusters themselves aren't moving through space in any special way. What's actually happening is that space itself is expanding. The distance between clusters increases not because the clusters are moving through space, but because new space is being created between them. It's the fabric of space that's stretching, carrying the clusters along with it. This distinction matters because it affects how we understand very large distances. Galaxies at the edge of the observable universe are receding from us at speeds greater than the speed of light, which sounds impossible. But they're not actually moving through space faster than light. Space itself is expanding, and the cumulative expansion across billions of light years adds up to an effective recession speed exceeding light speed. This is why the observable universe is 93 billion light-years across, even though the universe is only 13.8 billion years old. Space has been expanding while the light was traveling, stretching the distances between origin and destination. Second, people sometimes imagine the Big Bang as an explosion that happened at a single point, with everything expanding outward from that point. This isn't quite right either. The Big Bang happened everywhere at once. Every point in space was once part of that hot, dense initial state. The expansion isn't an expansion into something, it's an expansion of space itself. There's no center to the expansion. Every location in the universe sees every other location moving away from it. From our perspective, the Milky Way seems to be at the center, with everything receding from us. But an observer in Quipu would see the same thing, with everything receding from their location. Third, people sometimes ask what exists outside the universe. This question might not have a meaningful answer. The universe, by definition, is everything that exists. There might not be an outside for anything to exist in. Our intuitions about objects having outsides are based on our experience with objects within the universe, and those intuitions might not apply to the universe as a whole. Dark energy plays a crucial role in shaping structures like Quipu. Dark energy is the dominant component of the universe, making up about 68% of the total energy density. It has a peculiar property. Unlike matter and radiation, which become less dense as the universe expands, dark energy maintains a constant density. As space expands, the amount of dark energy within any given volume remains the same. This constant density means that dark energy's influence grows over time relative to matter. In the early universe, matter dominated. Gravity pulled things together, building structure. But as the universe expanded, matter became more diluted while dark energy stayed constant. Eventually, dark energy came to dominate. The transition happened about 5 billion years ago. Before that, the universe's expansion was decelerating, slowed by the gravitational pull of matter. After the transition, the expansion began to accelerate, driven by dark energy's repulsive effect. This acceleration has profound consequences for structure formation. Before dark energy dominance, gravity could pull matter together across increasingly large scales. Clusters grew, filaments lengthened. The cosmic web became increasingly complex. But after dark energy took over, this growth slowed. Gravity still works, but it has to fight against the accelerating expansion. At some point, the expansion will win completely. Galaxy clusters that are currently just beginning to interact will never merge. Filaments will stop growing. The cosmic web will freeze in place, unable to evolve further. This hasn't fully happened yet. We're in a transitional era where both processes are still active. Quipu is still evolving, still growing, though more slowly than it did billions of years ago. In the far future, it will reach its final state and remain there, isolated in an ever-expanding void. We don't fully understand what dark energy is. The simplest explanation is that it's a property of space itself, an intrinsic energy associated with every cubic meter of vacuum. This idea, called the cosmological constant, was first proposed by Einstein and then famously abandoned by him as his biggest blunder. Observations in 1998 showed that he was right after all, or at least right that something like it exists. But the cosmological constant has a problem. When physicists try to calculate its expected value from first principles using quantum field theory, they get an answer that's about 120 orders of magnitude too large. This is the worst prediction in the history of physics. Something is deeply wrong with our understanding of how the vacuum works. Other explanations for dark energy have been proposed. Perhaps it's not constant, but changes over time, in which case we call it quintessence. Perhaps it's a sign that gravity doesn't work the way we think on very large scales. Perhaps it's related to extra dimensions or other exotic physics. We don't know. Dark energy, like dark matter, remains one of the deepest mysteries in cosmology. So what does all of this mean? We've journeyed from the scale of a house to the scale of the largest structure in the observable universe. Along the way, we've encountered countless wonders along the way, from planets to stars to galaxies to clusters to superclusters to the cosmic web itself. Each scale reveals new patterns, new physics, new mysteries waiting to be solved. Quipu is the current endpoint of this journey, the largest coherent structure we know. It's a network of galaxy clusters spanning 1.4 billion light-years, containing trillions of stars and countless worlds. It formed over billions of years through the relentless action of gravity, assembling from tiny fluctuations in the early universe into a structure so vast that light takes over 1 billion years to cross it. And yet, compared to the observable universe as a whole, Quipu is small. It spans about 1.5% of the diameter of the observable universe. There's room for dozens of structures like Quipu within the volume we can observe. There's room for countless more beyond our cosmic horizon. We are small. Our planet is a tiny rock orbiting an ordinary star in an ordinary galaxy. Our galaxy is a modest spiral containing a few 100 billion stars. Our local group is a minor gravitational neighborhood. Even our supercluster is just one cell in the cosmic web, and yet we can understand. We can map structures billions of light years across. We can trace their formation back to fluctuations in the infant universe. We can ask questions about what lies beyond our horizon, even if we can never answer them directly. We are the universe become conscious, contemplating itself. That's remarkable. That's worth celebrating. The next time you look up at the night sky, remember that you're seeing just a tiny fraction of what exists. Behind every visible star are billions more too faint to see. Behind every galaxy are billions more too distant to detect. And connecting everything is the cosmic web, a vast network of filaments and clusters stretching across the observable universe. You're part of this. Your atoms were forged in stars. Your planet was assembled from cosmic debris. Your body is a temporary arrangement of matter that has been cycling through the universe for billions of years and will continue cycling for billions more. Thank you for joining me on this journey. If you enjoyed it, please consider liking and subscribing. It helps the channel grow and allows me to keep making content like this. Until next time, take care, keep looking up, and never stop wondering about the universe we call home. But actually, there's still more I want to share with you. We can go deeper into some aspects of cosmic structures that we've only touched on so far. Gravitational lensing reveals the hidden architecture of structures like Qipu. When light travels through the universe, it follows the curvature of space-time. Near massive objects, space-time is curved, and light bends as it follows that curvature. This bending of light by gravity is called gravitational lensing, and it's one of our most powerful tools for studying the cosmic web. Strong gravitational lensing occurs near very massive objects, like galaxy clusters. The bending is so severe that light from background galaxies is distorted into dramatic arcs and rings. Sometimes a single background galaxy is split into multiple images, appearing in several places around the lensing cluster. These Einstein rings and gravitational arcs are visually spectacular and scientifically valuable. Weak gravitational lensing is more subtle. It occurs when light passes through moderately dense regions of the cosmic web, not massive enough to create arcs, but still affecting the shapes of background galaxies. Instead of dramatic distortions, weak lensing creates tiny stretching effects, typically a few % change in a galaxy's apparent shape. Individually, these tiny distortions are impossible to detect. Any single galaxy might naturally be elongated for reasons having nothing to do with lensing. But when you measure the shapes of millions of galaxies and look for patterns, the effects of weak lensing emerge statistically. Galaxies behind denser regions of the cosmic web tend to be stretched in coherent patterns, aligned tangentially around the mass concentrations. By mapping these patterns across the sky, astronomers can reconstruct the distribution of mass regardless of whether that mass emits light. This reveals the dark matter skeleton of the cosmic web directly. We can see filaments stretching between clusters, even when those filaments contain no galaxies. We can measure the total mass of clusters, not just the mass of their visible components. We can verify that the universe really is dominated by dark matter, as other observations suggest. Weak lensing surveys are now a major enterprise in astronomy. The Dark Energy Survey has measured the shapes of hundreds of millions of galaxies. The Hyper-SuPrime-Cam survey in Hawaii and the upcoming Vera Rubin Observatory will extend these measurements to billions of galaxies. The European Space Agency's Euclid mission is specifically designed for weak lensing cosmology, measuring galaxy shapes across a large fraction of the sky. These surveys are revealing the cosmic web in unprecedented detail. They're finding filaments that were invisible in other observations. They're measuring the growth of structure over cosmic time, tracking how the web has evolved. They're testing our models of dark matter and dark energy against reality. For structures like Qipu, weak lensing provides essential information. It confirms that the clusters we see in X-rays are embedded in much larger dark matter halos. It traces the filaments, connecting clusters, revealing connections that would be invisible otherwise. It measures the total mass of the structure, showing that what we see in light is only a fraction of what's really there. Supermassive black holes play a surprising role in galaxy clusters. At the center of almost every large galaxy sits a supermassive black hole. These black holes contain millions to billions of times the mass of our own star, compressed into regions smaller than our solar system. They're the most extreme objects in the universe, places where gravity is so strong that not even light can escape. Supermassive black holes didn't just appear fully formed. They grew over billions of years by consuming matter from their surroundings. When matter falls toward a black hole, it forms an accretion disk, a swirling vortex of gas and dust spiraling inward. Friction within the disk heats the matter to temperatures of millions of degrees. making it glow brightly across the electromagnetic spectrum. Black holes with active accretion disks are called active galactic nuclei, or AGN. The most luminous AGN are quasars, which can outshine their entire host galaxy by factors of hundreds or thousands. A single quasar, powered by a supermassive black hole swallowing matter, can be visible across billions of light-years. In galaxy clusters, the central galaxy usually contains a particularly massive, supermassive black hole. This black hole often has jets, narrow beams of particles accelerated to nearly the speed of light, shooting out from the poles of the accretion disk. These jets extend thousands or even millions of light-years into the surrounding space, punching through the intracluster medium and creating enormous cavities filled with relativistic particles. These cavities are visible in X-ray images as dark bubbles in the otherwise bright glow of hot gas. They're some of the largest coherent structures produced by individual objects. Single black holes creating disturbances millions of light-years across. The energy released by these jets is enormous. A single outburst can release as much energy as a supernova, but spread over millions of years rather than seconds. Over the lifetime of a galaxy cluster, the cumulative energy from AGN jets can exceed the gravitational binding energy of the entire cluster. This has important consequences for the evolution of clusters. The hot gas in clusters should be cooling over time, losing energy through X-ray emission. As it cools, it should sink toward the cluster center, forming new stars. But we don't observe this happening at the expected rate. Cooling flows should be producing hundreds of solar masses of new stars per year in cluster centers. But the actual star formation rate is much lower. The explanation is AGN feedback. The jets from the central black hole heat the cooling gas, preventing it from collapsing and forming stars. The black hole acts as a thermostat, regulating the temperature of the cluster gas. When gas cools too much, it flows toward the center, feeds the black hole, triggers jet activity, heats the gas back up. This feedback loop maintains the cluster in a quasi-stable state over billions of years. Within Quipu, each of the 68 clusters has its own central galaxy with its own supermassive black hole. Some of these black holes are actively feeding, launching jets, carving cavities. Others are quiescent, waiting for new material to fall in. The collective activity of these black holes affects the entire structure, regulating gas cooling and star formation across billions of light years. Peculiar velocities reveal even more about cosmic structure. When we measure the redshift of a galaxy, we're measuring how fast it appears to be receding from us. Most of this recession is due to the expansion of space, the Hubble flow that carries all galaxies away from each other as the universe expands. But superimposed on this cosmic expansion are peculiar velocities, additional motions caused by the gravitational influence of nearby mass concentrations. If a galaxy is falling toward a massive cluster, it will be moving slightly faster toward that cluster than the Hubble flow alone would predict. If it's being pulled in the opposite direction, it will be moving slower. By measuring these peculiar velocities for thousands of galaxies, we can map the gravitational field of the cosmic web and infer the distribution of mass, including dark matter. This is how astronomers discovered the Great Attractor, a massive concentration of matter hidden behind the plane of our own galaxy. In the 1970s and 80s, astronomers noticed that galaxies in our region of space all seemed to be flowing toward a particular direction in the sky. Something massive was pulling them, but it wasn't visible because it lay behind the Milky Way's obscuring dust. We now know the Great Attractor is part of a larger structure called the Shapley supercluster, one of the most massive concentrations of matter in the relatively nearby universe. The peculiar velocity of our own galaxy, about 370 miles per second toward the constellation Leo, is caused partly by the gravitational pull of these distant mass concentrations. Peculiar velocities also reveal structure on smaller scales. The infall of galaxies into clusters creates distinctive velocity patterns. Galaxies on the near side of a cluster appear to be moving faster than the Hubble flow, falling toward us. Galaxies on the far side appear to be moving slower, falling away from us. This creates what's called the finger of God effect in redshift surveys, where clusters appear elongated along the line of sight. Within Quipu, the peculiar velocities of galaxies trace the gravitational influence of the structure. Galaxies are flowing along filaments toward clusters. Clusters are falling toward each other in the denser regions. The entire structure is in motion, rearranging itself under the influence of gravity, even as the expansion of space gradually slows this rearrangement. Cosmic magnetism also shapes the cosmic web in subtle ways. Space is not completely empty. Even in the vast voids between galaxies, there are trace amounts of gas and scattered magnetic fields. These magnetic fields are extremely weak, typically 1,000,000 times weaker than Earth's magnetic field, but they extend across enormous volumes and play important roles in the physics of the cosmic web. Magnetic fields are found throughout galaxy clusters, embedded in the hot intracluster gas. They're amplified by turbulence as clusters merge and evolve. They affect how charged particles move through the gas, influencing everything from heat conduction to the propagation of cosmic rays. The origin of cosmic magnetic fields is still debated. One possibility is that they were seeded in the early universe, perhaps during inflation or phase transitions in the first seconds after the Big Bang. Another possibility is that they were generated later by the motion of charged particles in galaxies and ejected into intergalactic space by winds and jets. Whatever their origin, magnetic fields are now recognized as an important component of the cosmic web. They contribute to the pressure that supports hot gas in clusters. They confine relativistic particles in the cavities carved by AGN jets. They affect the polarization of radio waves passing through the web, allowing astronomers to map their structure. Future radio telescopes like the Square Kilometre Array will map cosmic magnetic fields in unprecedented detail. By measuring the polarization of radiation from distant sources, they'll trace the magnetic field structure of filaments and clusters across billions of light years. This will add another layer to our understanding of structures like Quipu. The boundaries of cosmic structures are among the most dynamic and violent places in the universe. At the edges of galaxy clusters, fresh material is constantly falling in from the surrounding filaments, drawn by the cluster's gravitational pull. This infalling matter crosses a boundary called the accretion shock, where it's suddenly decelerated and heated to extreme temperatures. Accretion shocks are among the largest shock waves in the universe. They surround galaxy clusters at distances of several million light-years from the cluster center. As matter crosses these shocks, it transitions from the cool, diffuse gas of the cosmic web to the hot, dense gas of the intracluster medium. The transformation is violent and sudden, releasing enormous amounts of energy. These shocks accelerate particles to very high energies, creating cosmic rays. Some of these cosmic rays are protons and heavier nuclei, which can eventually escape the cluster and travel through the universe. Others are electrons, which spiral in the magnetic field and emit radio waves. The radio emission from these shock-accelerated electrons creates diffuse structures called radio relics, which mark the locations of merger shocks in galaxy clusters. Within Quipu, accretion shocks surround each cluster, and merger shocks occur when clusters collide. These shocks are processing enormous amounts of matter, heating it, accelerating particles, shaping the structure of the entire system. They're invisible to optical telescopes, but detectable in radio and X-ray observations. There's also a connection between cosmic structure and the origin of heavy elements. The atoms in your body, the carbon, oxygen, nitrogen, iron, and all the other elements heavier than hydrogen and helium, were not present at the beginning of the universe. They were forged inside stars and spread through space when those stars died. When stars exhaust their nuclear fuel, they end their lives in one of several ways depending on their mass. Low-mass stars, like our own star, will expand into red giants and then shed their outer layers as planetary nebulae, leaving behind white dwarfs. Higher-mass stars explode as supernovae, blasting their enriched material into the interstellar medium and leaving behind neutron stars or black holes. The most massive stars explode so violently that nothing remains. Supernovae are the primary source of elements like oxygen, carbon, silicon, and iron. They enrich the surrounding gas with these heavy elements, raising what astronomers call the metallicity. Over cosmic time, as generation after generation of stars form and die, the metallicity of the universe gradually increases. Galaxy clusters record this enrichment history. The hot intracluster gas contains heavy elements mixed in with the primordial hydrogen and helium. By measuring the X-ray emission from this gas, astronomers can determine its composition and track how metallicity varies across the cluster. What they find is that the gas in cluster centers has higher metallicity than the gas in cluster outskirts. This makes sense because cluster centers contain more galaxies, which have produced more supernovae, which have enriched more gas. But even the outskirts of clusters have some enrichment, suggesting that heavy elements have been spread across enormous distances by galactic winds and AGN jets. Within Quipu, the distribution of heavy elements tells the story of billions of years of stellar evolution. Each cluster has its own enrichment history, its own pattern of metallicity. Together, they record how stars have been forming and dying throughout this vast structure since the universe was young. Cosmic archaeology reveals what we can learn from the oldest structures. The universe hasn't always looked the way it does now. In the distant past, galaxies were smaller, more irregular, more actively forming stars. Clusters were less massive, still in the process of assembling. The cosmic web was denser, with shorter distances between nodes. By looking at different distances, we look at different cosmic epochs. Nearby structures show us the universe today. Distant structures show us the universe billions of years ago. This is cosmic archaeology, using light travel time to study the evolution of the universe. For Quipu, this means we're seeing the structure at a range of epochs. The nearest clusters are seen as they were 425 million years ago. The most distant clusters are seen as they were 800 million years ago. By comparing them, we can study how clusters evolved during that 375 million year span. What we see is that earlier clusters were generally smaller, still growing through accretion. Later clusters are more massive, having had more time to accumulate matter. The filaments connecting clusters were denser in the past, as less matter had been evacuated into the clusters themselves. The overall picture is one of gradual growth and concentration. This matches what we see in simulations of cosmic evolution. The cosmic web grows from the inside out, with the densest regions forming first and the less dense regions filling in later. By mapping structures at different redshifts, we're watching this process unfold. Cosmic variance is worth mentioning for what it means for our understanding. The universe is fundamentally a random place. The specific arrangement of matter in our observable volume depends on the random fluctuations that were present after inflation. A different random realization would have produced a different cosmic web, with clusters and voids in different locations. Different observers in different parts of the universe would see different structures. This randomness limits what we can learn from observations. We only have one observable universe to study. We can't run the experiment again with different initial conditions. This is called cosmic variance, and it's a fundamental limit on cosmological inference. Cosmic variance is particularly important for rare objects like Quipu. Finding one such structure in our observable volume doesn't tell us precisely how common they are in general. We might have gotten lucky, finding a 1 in a million fluctuation, or Quipu might be typical, and similar structures might be common throughout the universe. To deal with cosmic variance, astronomers run many simulations with different random seeds. They ask how often structures like Quipu appear across all the simulations, averaging over many random realizations. This gives them a sense of how unusual or typical the observed structure is. Current simulations suggest Quipu is somewhat unusual, but not impossibly so. Structures this large should appear in perhaps 1 in 100 or 1 in 1,000 similar volumes. Finding one in our observable universe is lucky, but not outlandishly so. We don't need to invoke new physics to explain it, though the possibility remains open. This journey is coming to a close, and some final reflections are in order. We began with a scale of a house, a space you can walk across in 30 seconds. We ended with Quipu, a structure 1.4 billion light-years across, containing billions of galaxies and trillions of stars. The ratio between these scales is beyond calculation, beyond imagination, beyond any number that has meaning in everyday life. And yet, both scales are real. Both are part of the same universe. The atoms in your house were forged in stars that lived and died billions of years ago, in galaxies scattered across the cosmic web. The structures we observe with our telescopes, Quipu and its cousins, are made of the same stuff as you and me and everything we know. This is the profound truth at the heart of cosmology and everything we've explored tonight. We are not separate from the universe. We are part of it. We emerged from it. We're made of it. And we're capable of understanding it, at least in part. The universe is vast beyond comprehension. But it's also comprehensible, at least to minds that evolved within it. Mathematics works. Physics works. We can describe the behavior of matter and energy across scales spanning dozens of orders of magnitude. This is remarkable and unexpected. There's no obvious reason why the universe should be understandable by creatures like us. Perhaps this is a clue about the nature of reality. Perhaps the universe is mathematical in some deep sense, and minds capable of mathematics can therefore understand it. Or perhaps we've simply evolved to be good at finding patterns, and the patterns we see in the cosmos are the ones our brains are wired to detect. We don't know. This is one more mystery among many. What we do know is that the universe is beautiful. It's structured at every scale, from quarks to superclusters. It evolves over time, changing in ways we can predict and understand. It contains countless worlds, most of which we'll never visit or even see. And it contains us, conscious beings capable of wondering about it all. Quipu is the largest known structure in the universe. It's a network of galaxy clusters spanning 1.4 billion light-years. It took billions of years to form and will persist for billions more. It contains more stars than there are grains of sand on Earth, more worlds than we could visit in 1 trillion lifetimes. And you know about it. You've spent time learning about it. That's a small miracle when you think about it. An arrangement of atoms on a small planet orbiting an ordinary star has become aware of structures spanning a significant fraction of the observable universe. The universe is looking at itself through your eyes. Thank you for being part of this journey through the cosmos. Sleep well, and may you never stop wondering about the cosmos that created you.